Now that we have introduced the concept of reservoir simulation and the role of data, modeling, and gridding, we move into the theory of reservoir simulation. In this section, I want you to focus on the physical laws behind the simulator. The software may look complicated, but at its heart it is built on very fundamental conservation principles. The first governing principle is conservation of mass. The idea is simple but very powerful. Mass cannot be created or destroyed in a closed system. In reservoir simulation, we apply this to a controlled volume within porous rock. The mass entering the volume, minus the mass leaving the volume, must equal the change of mass stored inside the volume. This gives us the foundation for flow equations in porous media. If more fluid enters a grid block than leaves it, mass accumulates and pressure or saturation changes. If more fluid leaves than enters, the block depletes. This is why mass conservation is one of the most important equations in simulation. Without it, we could not realistically track reservoir behavior. The next principle is conservation of momentum. In general fluid mechanics, momentum conservation is described by the Navier-Stokes equations. However, in reservoir engineering, flow through porous media is usually slow and laminar, so the full Navier-Stokes equations are simplified into Darcy's law. Darcy's law tells us that fluid flow rate depends mainly on permeability, fluid viscosity, and pressure gradient. In simple words, fluids flow more easily in high permeability rocks, more slowly when viscosity is high, and they are driven by pressure differences. This simplification is extremely important because it allows us to model subsurface flow efficiently while still capturing the essential physics. This slide reminds us that reservoir simulation solves flow equations in discretized grid blocks. Pressure and saturation are the two most central variables in many reservoir simulation formulations. Pressure determines the driving force for flow, while saturation tells us how much oil, gas, or water occupies pore space in each grid cell. You can think of the simulator as solving a huge network problem. Each cell interacts with neighboring cells in the X, Y, and Z directions, and wells create additional sources or sinks. The simulator must calculate how pressure and saturation evolve throughout this grid system at each time step. In most realistic reservoir problems, exact analytical solutions do not exist. That is why we need mathematical and numerical methods. Techniques such as homogenization and volumetric averaging help convert complex heterogeneous systems into tractable forms. Then numerical methods such as finite difference, finite volume, and finite element methods are used to solve the equations. This is a very important lesson for students. Most real reservoirs are too complex for closed-form solutions. Numerical simulation is necessary precisely because the real world is heterogeneous, multidimensional, and time-dependent. This slide explains why pressure and saturation equations are not straightforward to solve. If all coefficients were already known at the current time step, the pressure equation could be solved as a linear system. But in practice, many coefficients depend on changing variables such as saturation and pressure themselves. That creates nonlinearity. So what do? We use a first guess. We timeline some coefficients from the previous step, solve for pressure, then update saturation, and iterate. This is a common idea in numerical simulation. Use an approximate estimate, update the solution, and repeat until the system converges. This iterative structure is the backbone of many reservoir simulation algorithms. Here we see the IMP strategy, which stands for implicit in pressure and explicit in saturation. This is one of the classical methods in reservoir simulation. The idea is to solve pressure implicitly, which gives numerical stability, and then solve saturation explicitly, which is computationally simpler. The benefit of IMPS is that it balances efficiency and stability. Implicit pressure calculation can handle larger time steps more robustly, while explicit saturation updates reduce complexity. However, explicit saturation treatment may require smaller time steps to remain stable. So IMPS is a good example of a practical engineering compromise in numerical simulation. Now we move to upscaling, also called homogenization. Upscaling means replacing a highly detailed heterogeneous fine-grid region with an equivalent coarse-grid region that has effective properties. The goal is to preserve important flow behavior while reducing computation time. Why is this necessary? Because detailed geological models can contain enormous numbers of cells, and running full dynamic simulation on all of them may be too expensive. By upscaling, we make the problem manageable. But there is always a risk. When we average fine-scale details, we may lose some important behavior. So upscaling must be done carefully. This slide introduces pseudo-properties. A pseudo-property is an average or effective value used at the simulator grid block scale. For example, a single block may represent a large volume of rock with internal geological variability, yet the simulator uses one effective permeability value for that block. This concept is very practical. In reservoir simulation, we rarely model every tiny geological detail directly. Instead, we represent their overall effect through pseudo-properties. The challenge is that different averaging methods may produce different effective values, especially for permeability. Here we compare arithmetic, geometric, and harmonic averages for permeability. Arithmetic averaging is often appropriate when flow is parallel to layers. Harmonic averaging is often appropriate when flow is perpendicular to layers and low permeability layers dominate resistance. Geometric averaging is commonly used for more general heterogeneous systems. The key engineering message is that averaging is not trivial. The correct average depends on flow direction and geological arrangement. If we choose the wrong averaging method, the model may misrepresent how easily fluids actually move through the rock. This slide introduces relative permeability, which is central to multiphase flow. In a reservoir, oil, water, and gas share the same pore space. Therefore, each phase does not flow as easily as it would if it occupied the rock alone. Relative permeability measures the effective flowability of one phase relative to the absolute permeability of the rock. On the graph, as water saturation increases, water relative permeability increases and oil relative permeability decreases. This makes intuitive sense. When more water occupies the pores, water flows more easily and oil flows less easily. Relative permeability curves are essential inputs in multiphase reservoir simulation because they control how phases compete for flow through the porous medium. Transmissibility measures how easily fluid flows between two grid blocks. It depends on rock properties like permeability and area, fluid properties like viscosity, and the pressure difference between the blocks. In simple terms, transmissibility tells the simulator how strongly neighboring cells are connected hydraulically. This concept is extremely important because the simulator is effectively a network of grid blocks exchanging fluids. If transmissibility is high, fluids move more easily between cells. If it is low, flow is restricted. So transmissibility plays a major role in pressure communication, fluid displacement, and well performance. Now we move to fluid modeling. The black oil model is a common approach for simulating immiscible 2- or 3-phase flow in porous media. In this approach, the phases are treated in a simplified way. Gas can dissolve in oil and water to some extent, but the full detailed chemical composition is not tracked explicitly. This model is very useful for conventional reservoir engineering problems such as natural depletion and many secondary recovery processes. Its main advantage is simplicity and computational efficiency. When phase behavior is not too complicated, black oil models are often sufficient and widely used in industry. In contrast, the compositional model explicitly tracks the chemical composition of the phases. This is necessary when pressure volume temperature behavior is complex, when phase changes are important, or when injected gases such as CO2 significantly affect fluid behavior. Compositional modeling is essential for gas condensate reservoirs, miscible gas injection, and CO2 storage projects. It can represent how different components partition between gas, oil, and water phases over time. This makes it more physically realistic for complex systems, although also more computationally demanding. So again, the engineering choice depends on the problem.